Good afternoon, as usual. First, let's check somebody from home if you can hear. Can you hear? Anybody? Anyone? Again, anybody from home, can you write if you can hear me? Or okay, then we're set. Okay, so good afternoon. This is not the slide that I want to show now. Today we finish talking about the Gaussian models, and then we introduce a new classification model for discrete data. So last week and yesterday in the laboratory, we discussed the multivariate Gaussian model. That is a model where we assume that the samples of each class are modeled by Gaussian densities with one mean and one covariance per class. So each class has its own set of parameters. We've seen how to compute the maximum likely solution for the estimation of the parameters of the model. So we have our samples, and we have said we need to essentially fit one Gaussian to the samples of each class. So we estimate mean and covariance matrix of the samples. We have seen that these correspond to the maximum likely solution. Then we have seen how to perform inference. We did it yesterday as well. We've seen for the multi-class problem, we would simply compute class posterior probabilities using the class conditional, that is what the model is able to provide for all classes, and the prior. So we test all hypotheses, and then for each hypothesis, we compute the density that the point would have if it belonged to that class, to the class I'm testing. This combined with the prior probability gives us the likelihood that the point that we observe the point and we observe the class label that we are making the hypothesis for, and then we divide by the marginal and we obtain the posterior probability. And then for the moment we said we just select the class that corresponds to the highest posterior probability. Then we've seen that for binary problems we can represent this how as a comparison of a score that is called log likelihood ratio, behaves like a score. So it's a value that the higher it is, the more it favors class 1, the lower it is, the more negative it is, and the more it favors class 0. This score represents the log likelihood ratio between the two hypotheses, so the likelihood of the samples given the hypothesis 1 and given the hypothesis 0. And then we perform classification by comparing this likelihood with a threshold, and the threshold depends on the prior probability. So pi is the probability of class 1. We have also analyzed how this model performs in terms of separation boundaries. So what we obtain if we set equal to a threshold, remember that we said that above a threshold we select class 1, below we select class 0. So when those points x for which the log likelihood ratio is equal to the threshold are on the separating surface between the two classes. It's the boundary between the two regions in space. For example, we have seen that if we set t equals 0 for this problem, the separation boundary corresponds to this set of curves. Here is class red, and outside is class blue. And we've seen that this kind of models are able to provide separation surfaces that are quadratic, because the log-likelihood ratio is a quadratic form. Then we have extended the model. Well, here we extended the model. We have made two approximations of the model that we can use when it's difficult to estimate the full covariance matrix per each class. The first approximation is useful when we can imagine that the different components of the feature vectors are almost independent. If they are almost independent, I can assume independence, and then I can factorize over the components my likelihood. We've seen this is called naive Bayes model. And with the naive Bayes model, we've seen that essentially what we do is we fit a univariate Gaussian model to each of the components on its own, and the result, again, for Gaussian models, corresponds to a, again, multivariate Gaussian model, but this time with a covariance matrix that is diagonal. So we can imagine that essentially what this model do is it forces covariances to be zero. Why? Well, remember that for Gaussian densities, independence implies correlation zero, but also correlation zero implies independence. This holds only for Gaussian data, distributed data. So essentially, zeroing the covariance values, those that are outside of the diagonal, corresponds with the Gaussian model with the independence assumption. So the independence assumption is equivalent to saying that the covariance between the different components is zero, and the model is indeed doing exactly that. It's zeroing, so rather than estimating these values, these are assumed to be zero because our model assumes that the features are independent. And here we have the variances, that is the diagonal of the covariance matrix. The benefit is that if we have lots of data, we need to just estimate. So if we have few data compared to the dimensionality of the data, we need to estimate only a set of the parameters. We do not need to estimate all the covariance terms, which means that our estimate will be typically more robust. Of course, this works only when the assumption is accurate. If I have, for example, I compute my empirical covariance matrix and I get that the empirical covariance matrix looks like this, this means that between the components 1 and 2 of my dataset there is a strong correlation, then the naive Bayes assumption will probably not work very well. What does it mean? This covariance matrix, it means that the points are essentially aligned over a direction that is not the principal one. Diagonal covariance matrix means that my estimates of the covariance matrix have axes that are aligned with the principal axis, which means that if I try to fit a naive Bayes model to this data, this is what I would get, the blue one with the full covariance, so the MVG. The naive Bayes model is trying to do an approximation of what it can do, but it can do only approximations with ellipses that are oriented along the principal axis. So I will estimate a covariance matrix that look like this, which is not a good estimate because it says that here, according to the naive Bayes model, here there should be points in space, but you see that according to the training set, there are no points in space in that region. So it's giving too much weight to points, to space. It may give too much weight to places where there are no points, or vice versa, it can have low real density in regions where we actually have a larger amount of samples. Of course, if my samples have components that are almost independent, like in this way, then my naive Bayes model will work well and will actually find the right solution. Now, when it's useful when I know that this holds, but for example, I have few samples like this. If I try to do an empirical covariance matrix on this data, I will probably get something that looks like this. But if I know that this holds, then the naive Bayes model can do better because it can it needs to just estimate the variance along the directions. It will ignore a correlation that I would estimate because I have few samples, so it looks like they are correlated because they are few, but I actually know from my problem that this is not true. It's just an artifact of the fact that I have few points. If I had more, they would look like this, and I would see that there are no correlations between the two features. So in this sense, naive Bayes can help getting a more robust estimate. Of course, if I know that there is strong correlation between the features, then probably naive Bayes will not work that well. Then we have seen a second model, the tight covariance model, where essentially we assume that the samples of each class share the same covariance matrix. Well, not the samples, the distribution that describes each class share the same covariance matrix. This is equivalent to say that for all classes, sigma C is equal to a single value, sigma, single matrix, sigma. When do we use this? We use this when we have few points with respect to the number of classes, so we have few points per class, but there are reasons to believe that the way the points of each class are organized with respect to the corresponding class mean is similar for the different classes. So when I can say that for each class, I have a mean of that class, which represents the class, and then I have a spread of my samples around the mean that does not depend on the specific class. We made, for example, the example of face identification, face recognition. We can imagine that each class is a person. We can imagine that each sample is a picture of a person. I may have few pictures of a person, but I can imagine that there is an average picture that represents that person, and then as a first approximation, I can imagine that the differences that I have in my pictures are due to phenomena that do not depend on the person. For example, the lighting, the background, the camera, all these factors do not directly depend on the picture that is depicted, but I can imagine they affect in a similar way pictures of different people. An image will be dark or light depending on the light source that you have, regardless of who is depicted in the picture. So if I imagine that, for example, having a brighter image, a brighter light brings my average image in this direction, then we will do a similar thing for all people. It will move the average picture in a similar way. So I can imagine that the effects that describe why the images are different from the class mean do not directly depend on the class itself. So they are, as a first approximation, independent of the class. Then if this is the case, I can exploit the information that I get from all these classes jointly to estimate what is the covariance of this shared covariance for all classes. And we have seen that the result is the within-class covariance that we estimated for LDA. In this case, what do we have? Well, if we look at what the model is doing, we see that it's estimating one mean for each class, and then the covariance matrix of each class is the same. You can see that they are organized in the same way. So this works well when the classes typically have similar covariance matrices. Otherwise, it will try to do a, we've seen the within-class covariance matrix is a weighted average of the within-class of the covariance matrix of each class. So if this is not the case and I have classes which have very different covariance, then what the model will do, well, the MVG would fit one covariance per class. This model would try to do something that is an average of the two. So we'll fit a single covariance and use it for both classes. So in the end, it will be an average of the two covariances, weighted by sample average, we have seen. But if we have a similar amount of samples per class, it will look like an average of the two covariances. Is this good or not? Well, it depends. For an example like this, it will work well because in any case, the classes are well separated. So even if I don't get a good estimate of this outlier of these positions, I still am able to separate the classes. If I have a problem where, for example, I have two classes like this, what will happen if I apply the multivariate Gaussian model? It will estimate a mean for the red and the mean for the green. They will be pretty much the same. And then what covariance will use? Well, for the red, it will estimate an average of the two, and for the green, it will also estimate an average of the two. So according to the model, the two classes become very, very similar. So in this case, the tight model is not able to separate the classes anymore. Remember that if I have, for the two classes, the same Gaussian density, when I compute the likelihood, I will say that the probability for a sample is almost the same for the two classes. We have seen that, and we will come back to this in a moment, the tight model corresponds to linear separation surfaces, and indeed we can see here that whatever we use as linear separation surfaces, we will not be able to solve the problem. So from the point of view of the distribution, we can see that it's not able to capture the differences in the distribution that are useful for classification, because it ends up estimating the same density for both classes. But actually what matters here is that there are these regions where there are only red points, and there are these regions where there are only blue points. From the point of view of the classification rule, we know it's linear, and we know that no matter how hard we try, we cannot distinguish those two classes with a linear surface. So that confirms that the model will not work well. On the other hand, the multivariate Gaussian model would do what? In this case, it would fit like this, the two densities, and this would correspond to separation rule that would look like this. So there will be regions where the samples are assigned to the red, and regions where they are assigned to the green. In this case, the two classes have the same mean, but the different covariance matrix allows me to decide to which class a point that lies here belongs to. A point that lies here is more likely to be from the green class. Then, of course, I need to factor in the prior probability. So the prior probability will move where these surfaces are. But, for example, if the prior probability is the same, the separation rule will look like this. It can do quadratic separation surfaces. Okay. Questions up to here? Okay. Then, for this picture, I don't think that I commented but last time, but this is just the multivariate version of the tight model, and as well here we can see that the class boundaries are linear. So the separation boundaries between two adjacent classes become linear, as for the binary version of the problem. Now we have said that, well, we have said already in the laboratory, I don't remember if we did this slide last week, but if we did it very quickly, so I will do it again. I will go on it again. But yes, in the laboratory, if you attended, you saw that at the end of the tight model, there was a suggestion to check whether the model was giving the same results as LDA. And we have seen that the within-class covariance that we use for the tight model is indeed the same covariance matrix that we use for LDA. So that was involved in estimating the LDA direction, LDA for classification. So let's again consider LDA as a binary classifier and see how it relates to this model. LDA we've seen is optimized to, looks for a direction that optimizes this quotient that says that the projection direction of LDA should result in high separation between the classes, high compared to the spread inside each class. So large projected between divided projected within, which we can express in this way. And the SW that we have here is exactly lambda to the power of -1, so the within class covariance of the tight model. SB we didn't show, but SB can be expressed, or well, I think we showed, but we didn't prove it, can be expressed in this way. So as a constant times the difference of the two means times the difference of the two means transposed. This holds for a binary problem. It's just a matter of taking the definition of the between class covariance and rewrite, manipulate it a bit. Then since we are optimizing the ratio, this constant does not depend on W and does not depend on W, so we can just throw it away. It doesn't really matter what's the value. To solve the problem, we can look for, we can obtain the generalized eigenvalues of this of the LDA problem, and we have seen that once we have solved the LDA problem, essentially, this we didn't see because we skipped that classes, so let's skip this. But we have seen that once we solve the problem, we can show that a solution of the problem corresponds to a W that is proportional to lambda mu1 minus mu0. And then we said we compute W transpose X for a test point, which means, let's write it in this way, it's X transpose lambda mu1 minus mu0 times some constant. And the constant derives from the fact that I'm looking for an eigenvector and then I can choose the norm of the eigenvector freely. But that's, again, not important. What matters is that the LDA solution was obtained by projecting X over a direction that looks like this, and then comparing this with a threshold. Now, if you look at this term here looks the same as the B term that we have for the log-likelihood ratio for the tide model. What does it tell us? It tells us that the kind of decision surface, remember that the decision surface then depends on the threshold that we used. For LDA, we said, okay, let's project over the LDA direction, and then we will see how to find a threshold. So we left free the choice of the threshold. We didn't analyze how to choose the threshold. But if this W is exactly lambda mu1 minus mu0, then the LDA solution was compute X transpose lambda mu1 minus mu0 and compare it with a threshold. And again, we said we will see how to select a proper threshold. But these kind of decision rules are the same decision rules of the tide model. We know that in the tide model, this corresponds to the log-likelihood ratio for X. Well, actually, this plus the constant C. So the log-likelihood ratio for X is this term plus a constant C. So what we have here is the log-likelihood ratio for X minus this constant C. And then we said we compare it with a threshold. Again, this corresponds to comparing the log-likelihood ratio with a threshold. Let's move C on the other side. We are comparing our log-likelihood with a threshold T prime. Since we didn't define T, we still don't know what is the T prime that we should use. But from the tide model, since it's a generative model, we know that the prior here, the threshold here should be the prior minus the prior log odds. So essentially, we can see that the tide Gaussian model gives us the same decision rules as the LDA model, and additionally, it tells us what is the optimal threshold. We will prove that it's optimal later next week. But it gives us the optimal threshold to separate our classes based on the prior information that we have. So the tide model corresponds to the, let's say, probabilistic version of LDA, and it inherits many of its, well, it shares many of its assumptions. For the tide model, we said the assumption is that the within class covariance is the same for all the classes. Indeed, we didn't say it, but that's also the criterion that is required by LDA to be optimal. LDA, to give you an optimal projection direction, requires that the within class covariance of the classes is the same. So LDA is actually useful as a way, as a classifier, and in general also as a dimensionality reduction approach, when the covariance matrix of the different classes is the same. And it's actually a non-probabilistic version of the tied Gaussian model. So we can conclude that LDA essentially assumes that the classes can be modeled by Gaussians with a single shared covariance matrix. For this reason, sometimes in the library you find that the tied Gaussian model is directly called LDA because actually they are very, very similar. In the same way, the multivariate Gaussian model, you may find it called quadratic discriminant analysis. Why quadratic? Because we have seen that LDA and tied model are essentially the same thing and they give linear separation rules. The generic multivariate Gaussian model gives quadratic separation rules, so by extension we call it also quadratic discriminant analysis if you want to use the naming that was used for LDA. But the two models, well, I don't like using this name, but you can find it used. But in any case, for LDA in the tied model, we essentially have the same kind of separation rules. Of course, in LDA, we didn't know how to select the threshold. Now, with the Gaussian model, we know how to select the threshold that is optimal for our task. Then, when we use the Gaussian classifiers, again, we need to make some practical considerations as when we use LDA and PCA. For example, we have seen that LDA suffers from high-dimensional data. Why? Because I may have directions where the within-class covariance is almost zero for LDA. This is even worse for the multivariate Gaussian. For the tied, it's the same issue. It's the same model, so it's the same issue. The multivariate Gaussian is even more problematic because the multivariate Gaussian requires one covariance matrix per class. So if the overall within-class covariance is singular, of course it is also for each class, but it may be singular for some classes just because for some classes I may have few points. So it's even, and I have even higher troubles than I have with the standard, with the LDA model. Again, maybe we have seen how to simplify the estimation for some use cases, but the simplified models work well if the assumptions are met. If the assumptions are not met, then these models may actually not work well enough. So that means that we may want to still use multivariate models because we know that our samples have orientations that do not allow us to use neither the naive nor the tied model, but the dimensionality of the space is too large to estimate the full covariance matrices. So in this case, a simple thing that I can do is I can use PCA to reduce the dimensionality. This solves these two first problems. It removes directions with very small variance, which will also have very small within-class variance. So the class covariance matrix will be singular, but PCA removes directions where this is singular. And it also addresses the second problem if it's able to throw away directions that do not contain discriminant information. Of course, this we don't know in advance. So we may need to figure out what is a good value for the PCA subspace to avoid throwing away too much useful information. If we have reasons to believe that our assumptions are accurate, then we can also try the simplified models that we have discussed. This I will say a couple of words after. Here, for example, we can see the error rate on the MNIST for the different models. For the moment, we didn't discuss this, so let's just ignore this line. We have the tied Gaussian. The tied Gaussian works as LDA, and it shouldn't be surprising now that these two values are the same. The tied Gaussian works as LDA. We have seen it works as LDA for a binary task. It gives the same separation rules. If I use LDA as a dimensionality reduction, as in this case, to reduce the dimensionality, in any case, we can prove that the space that contains the C-1 directions that I can find for LDA, so all the maximum number of LDA directions that I can find, that space contains all the information that is required to make inference according to the tied Gaussian model. So if I have C classes, I apply LDA to go to c minus 1 directions and then I apply the tide model over this data, I will get the same results as if I applied the model over the original samples. The LDA subspace contains all, the maximum size of the LDA subspace contains all the information that is exploitable by the tide Gaussian model. So it's not a chance that these two are exactly the same. They must be the same. If they were not the same, there would be something wrong in the implementation. Then we can see that essentially these are results similar to what we got with LDA. With LDA, we were using a threshold that we can show is the same threshold that we would use if the prior probability for the class, well, for the binary problem, we're using a threshold that is similar to the one that corresponds to the same, sorry, no. Let me close the parentheses. Let's go back to what I was saying. So the tide model is able to exploit all the LDA direction and gives the same results. Here we can see that when I apply, notice that here I apply PCA before LDA because I need to avoid singular within class covariances. That's the same reason why I need to apply PCA before any of the Gaussian models, because we already know there are directions where the within class covariance for the different classes is 0 for MNIST. We have discussed it when we did LDA. For example, the top left corner of all the images is white, which means it has the same value for images. It means that there is no variance over the direction. So the within class variance over the direction will be 0. We can see that in this case, reducing to 100 gives us some results. If we reduce more with PCA, we actually lose performance. With LDA, we don't, for the reason that we just said. Then we can look at the full Gaussian model. The full Gaussian model shows us that we already, with 100 PCA direction, obtain much, much better results. This suggests that the tide assumption is probably not correct. The spread inside each class is probably not the same for all the digits. These are the samples that represent digits. The way each digit differs from an average digit, so the ways I write one differ from an average one, are different from the ways that how I write zeros would differ from an average zero. So the same covariance structure cannot capture all these variations correctly because they would correspond to different covariance matrices in space. And here we see something that didn't happen before. We can see that if we reduce with PCA more, this time we didn't observe it in the first example that we took, but that we gave. But here we can see that PCA is actually helping my classifier. If I reduce to 50 directions, my error rate goes down from 4.3 to 3.6, which means that these 50 directions are a subset of the 100 ones. This means that the 101 contains all the information that is already in the 50 PCA, first 50 PCA dimensions, plus other information that makes my estimate less robust because of the larger number of covariances that I need to estimate. It increases the number of parameters that I need to estimate, and it reduces the robustness of my model because it will find covariances that are just spurious effects of the small limited number of samples. On the other hand, if I reduce too much, I again increase the error rate once more. I'm throwing away too much information. PCA doesn't know what it should keep and what it shouldn't for the classifier. Here it's removing too much information, and then I start seeing a decrease in my performance. So this shows that for this task, looking for an optimal M is relevant because it can give us a significant improvement with respect to just trying large values for the PCA. Finally, we see that the naive Gaussian model does not work that well. It means that probably, well, we can't assume independence between the components. Is it reasonable? Yes, it is. Let's look at an image. If I have a picture of a 1, how will it look? Like this. So that means these are the different pixels. If I have a pixel that is black, there is a good chance that the neighboring pixels will also be black. If I have a pixel that is white, there is a very high chance that the neighboring pixels will also be white, which means that there is a strong correlation between the different components of my feature vector. When one component is 1, there is a very high chance that the neighboring components will also be 1. When a component is black, there is a good chance that the neighboring pixels will also be black, which means that there is a strong correlation between the different components. Naive Bayes assumes that each pixel is independent of another. So the fact that here I have a white pixel doesn't tell me anything on the color of the neighboring ones, which may be with the same probability, well, not with the same probability, but they can be black or white with the same probability, given that this is white, the central one is black, or the central one is white. So the color of the inner pixel does not affect the probability that a pixel that is nearby will be black or white. But this is not true, because if we know a pixel is white, then the probability that the neighboring is white is also large, while if we know that a pixel is black, the probability that the neighboring pixel is white becomes low. So it depends on the neighbor. So they are not independent. And indeed, assuming independence, we obtain some results, but not the best one. Then finally, there is this naive tie that is the naive, where I also assume that the variance of each class is shared. So for each component, I assume that the variance is shared along the classes. Again, this gives us the same result. We didn't explain why, so I will just say one word, but we didn't explain it for LDA, so I will not go into the details why this happens. Our implementation of LDA transforms our data, when we use it to reduce the dimensionality, in a way that if I compute the within covariance over the transformed data, it will be the identity. That's by construction of how we solve the generalized eigenvalue problem. This means that if the within class covariance is the identity, it's diagonal. So if I use a naive Bayes model on top of that, I will get a model that performs the same as the original model before, as a tied model in the same space, without the rotation before, well, as the tied model in the original LDA space. Because the tied model would still estimate a covariance matrix that is the identity by construction. Let me see. But since we didn't see this makes less sense, probably. Now, last thing, then we move to the next topic. Sometimes our Gaussian assumptions do not work well for our data. Why? Because we may have data that cannot be modeled well by Gaussian density. For example, if I have an histogram of a feature that looks like this, I can try hard as I want, but I will not be able to fit a Gaussian density on that one. We see that if I try to fit a Gaussian density, we give high density where there are actually fewer samples, and low density where actually I have lots of samples. And in this case, it will even give density in places where there are no samples at all. And looking at the histogram, probably these features are between 0 and 1 because they are pixel values. So it doesn't make sense that the value for the pixel is 1.2. So it will give me a density for samples, for values that are not even in the domain of my task. How do we address this problem? Well, one possibility is we use a feature, a density model that is suited for this data. So for example, a density model that can model densities in this way. Another alternative, and we will not do the second one, it may be possible, as we did for PCA. Remember, we did PCA and LDA, we said when linear models are not enough, we can transform our data in a way that maybe linear models are good for the transformed data. This holds true also for this kind of models. Sometimes making a transformation of the features, transform my features into something that then can be described in terms of Gaussian densities in an accurate way. So sometimes transforming the features is a way to make a simple model work for something that looks like a complex task. Again, we will not do this. We will just see another model at the end of the course that is able to approximate the density for this, but we'll do it at the end. Okay, questions on this part? Okay, then we can move to a second task, a second example of a generative model. For the moment, we have used a generative model that is suited for continuous data. Gaussian densities are continuous densities, so they represent the density for continuous random variables. We now switch to a model that can be used for discrete random variables, so for discrete values, for dataset where the features are discrete rather than continuous. We see a simple model, and of course, then we can extend this. Now, we have a problem that is characterized by discrete features, and for the moment, we assume that there is only one feature in our dataset. For example, here we have a picture of cats. The task that we will use is, given the color of the fur of the cat, we want to identify its gender. So each sample is one cat described by its color. The color is a discrete attribute because it can take only a finite number of values. And it's a one-dimensional sample because we have only one feature. So the simplest case that we can make. We'll see why we make it simple, because making it with more features, we will see, makes things complex very quickly. And the goal is, again, for the moment, we consider a binary classification problem, the gender of the cat, but what we say, what we will say can actually be applied to a generic classification problem. In most cases, we write expressions for a problem with k classes. The example will be 2 classes, but we can work with k classes in a similar way. So we have our categorical feature, that is the color of the cat, and we have a label sample. And what we want to answer is, given a color, can we predict what is the gender? Now look, this is possible because there are some colors of the fur that appear more often in some genders rather than in others. For example, you have cats that have 3 colors, which are essentially all females. Males with 3 colors are very rare, so that is a discriminant value. If we know that a cat has 3 colors, there is a very high chance that the gender is female. Maybe for the other colors it's not that relevant, I don't know, but in any case this gives us, it's just an example that gives us some values for the feature that we can work with. So we have our dataset. The dataset consists of collections of color and class. So for example, we may have we observe one white cat that was male, then one white cat that was female, one black cat male, one orange female, and then let's say an orange male. Or let's make it female, so we have 2 examples of the same color. So this is what we collected. Of course, we may assume that we have many more of these samples. From this, we want to create a model that gives us the answer, what is the probability of female, for example, given that the color is orange. And then the same for male. Once we are able to answer to these 2 questions for every color, then given a color, we can predict. So a test sample will be the color of a cat we want to predict. Given the color, we can say what is the gender of the corresponding cat. Now, as usual, we assume that samples given model parameters are IID. So knowing the color of a cat will not tell me, if I know well, once I define the model and I've defined the probabilities that describe the likelihood that I observe a color in a given gender, then knowing the color of another cat will not give me any additional information. What does it mean? It means that our model must compute probability of female given orange. We want to do this through a generative model. It means that we need to model the probability of orange given female, the probability of black given female, and so on. So for each class, we have that the possible outcomes are white, black, let's make just orange. Then we need to create a model that, given a value of the feature, for each class, tell us what is the probability of the feature given the class. That's the same we did for the Gaussian model. For the Gaussian model, we described each class in terms of a class conditional density that gave us the likelihood that we observe a value x when the class is C. There, x was a continuous function, so we had a continuous density that we model with a Gaussian distribution. Here we have a discrete feature, so we have a full model once we are able to compute the probabilities, probability of white given female, probability of black given female, and probability of orange given female. Once we have these three values, these are the only values that the feature can take, once we are able to compute these terms, we have fully specified the model for the female class. For any value of the feature, I can compute the corresponding probability. That's the same as in the continuous case. The Gaussian density, for any value of x, I can compute the corresponding likelihood. Discrete, for any value of x, which can be white, black, or orange, I can compute the corresponding likelihood. In this case, since it's discrete, it's actually also a probability. So here we use the word probability. So P, because these are actual probabilities. Now, I need a model that allows me to compute these values. The simplest model that I can do is actually simpler than what we have done before. I can say that I have a model which has three parameters, and the parameters are exactly, for the female class of course, are exactly the values that I want to compute. So here what I do is I say that the model is parameterized by three values, and these three values are exactly the probabilities that I want to compute. So if somebody gives me these three values, then these three values would tell me what is the probability of white given female, black given female, and orange given female. These are my models. So the model is very simple. The model doesn't give me a complex formula to compute the probabilities. The model is expressed directly with parameters that correspond exactly to the values that I want to compute. I can do it because it's discrete, so I have a limited number of values here. For the continuous case, I could not, because I would need to define, if I wanted to do it for the discrete, I would need to define for all possible values of x, the value that I want from the likelihood. So essentially, I would need to express the values for all possible inputs. These are continuous, so they are a dense, infinite number of values. Here, the possible values are just three, so I can easily say those three values are themselves the parameters of my model. So in this case, the model is very simple, and the parameters describe directly the quantities that we want to compute. Of course, this is for one class, the female class. If I have two classes, as in the Gaussian case, I need to define a model for the class conditional probability, in this case, for each class. So for the female class, I will have the three set of parameters: probability of white given female, probability of black given female, and probability of orange given female. This corresponds to exactly the probability of white given F, of black given f of white of orange given f. And then I will have for the male class a second set of parameters, probability of white m, black male, orange male. The probability of white given male, probability of black given male, and probability of orange given male. Notice that this is not the only choice. I could make more complex model where these values are a function of the color of X, the color, and some other complex set of parameters that, given the color and this set of parameters, computes these terms here. So this is not the only choice. I could make a model that looks more similar to the Gaussian model where the probabilities are a function of some parameters. Here, we are doing the most trivial case where this function is trivially the function that, given the parameters that are the three probabilities, will just select the one that I need for my computation. So this function, if this is theta, my function of color C parameter theta will just select pi using based on the color for that gender. So essentially, this can be seen as a very simple instance of a general way of expressing the model. Given a model that has some parameters, the model, given the color, will, using the parameters, select what's the probability of white of that color given female. In this case, the model is very simple because the parameters themselves are already the values that we want to compute. Now, we will not see more complex model than this, but just know that this is just the simplest instance that we can do for this kind of models. The parameters themselves are the quantities that we need to compute to describe the class conditional likeness. Of course, in this case, these parameters are not completely free. They represent probabilities, so inside each class, the values of the parameters should add up to 1. So if I take the pi w for the female, pi black for female, and pi orange for female, and white, black, and orange are my only colors, the sum of these must be 1 because they represent the complete space of options. There's a probability of white or black or orange. So the full probability must sum up to 1. Being white, black, or orange are exhaustive and do not intersect in terms of probability space options, so these probabilities must sum up to 1. And the same for the male. So for any class C, the sum of the corresponding parameters must be 1. Now, we have defined the model. Once we know the parameters, we will see that we can use this to make inference. How? Well, let's imagine that I have a cat, and then we will see it again, I think, in the slides, but let's imagine that I have a cat that is orange. How can I predict its class? Then I will want to compute probability that is female given orange, and probability that is male, that the class is male given orange, which is what? Probability of orange given female times probability of female divided probability of orange. And this is probability of orange given male times probability of male divided probability of orange. And how do we compute this? Well, this is, if I have the model parameters, this is pi orange f. So the numerator here, the first one will be pi orange f times the prior for f divided by p of orange that we will see again, we don't really need to compute. And the denominator and the second term here will be pi orange male times p of male divided p of orange. Notice that P of orange, if I want to compute it, P of orange is equal to the sum of the two numerators. So it's the joint probability of orange and female plus the joint probability of orange and male. If I want to compute it. So once I have these two numerators, I have everything that I need. But these terms here are the model parameters, so if I have the model parameters, we will see how to estimate. But for the moment, imagine I already solved the estimation problem, so I have the model parameters. I just need to plug in the prior information, but the prior information we have seen, we will have somebody who tells us what is the prior for this task. So for this specific application, what is the probability that one cat is male or female? For example, if there are no gender preferences, we may say that it's 1/2. And then we have everything to compute the class posterior probabilities. In this case, the class posterior probability will be proportional to the likelihood, so to the parameter pi that we have estimated. So if pi for the orange female is larger than the pi for orange male, in this case with the same prior probability, I would say that the class is female. So an orange cat for me is more likely to be a female cat when the prior probability for the two classes is the same. So inference, once we know these values, is done in the same way as the Gaussian models. From the class conditional likelihood, we build the joint. Then if we want, we compute the marginal, but we don't really need to compute the marginal. But in any case, once we have all the joints, computing the marginal is trivial because it's just a sum of the joint. So we need to compute the joint, which are the class conditional times the prior, but the class conditional is described in terms of the model parameters directly, so we need to just select the model parameter that corresponds to that class conditional likelihood. So for example, P of orange F is described by this parameter. And then combining all this together will allow us to compute class posterior and make inference exactly with the same criteria that we use for the Gaussian model. Maximum posterior class probability, that's the label that we will output. It remains to see how we estimate the model parameters. We need to figure out what is the value that we will use for the different pi's. Now, I anticipate that the results will be very intuitive. We have seen when we were doing a similar problem 2 or 3 weeks ago, we were trying to estimate the probability that a coin toss would give head. And we ended up saying that a good estimate, if we have lots of tosses, corresponds to the frequency of the heads. Now here we have a discrete problem, and this represents probabilities of whites inside the female class. So with a frequentist approach, I can imagine that this probability will, there is a good chance that we will correspond to the frequency of the white fur in the female class. If probabilities represents the frequency of some events, I can imagine that the probability of white given female is the fraction of white cats that I have in my female class. This is the correct answer according to the maximum likelihood criterion. We will prove it because we show how to apply maximum likelihood to this case, and then we'll do the derivation and show that this is indeed the case. But pay attention that as for the coin toss problem, the maximum likelihood solution is not necessarily the best solution. We have discussed that the maximum likelihood solution, when we have few samples, is not correct because the frequency estimate doesn't really work. And we will see that there are similar issues with this kind of models when we do the maximum likelihood estimate. Now, to get there, let's see, before we get to the issues, let's verify that our frequency corresponds to a maximum likelihood estimate. We have said the maximum likelihood estimate has good properties, it's consistent, and it converges quite quickly according to the frequentist framework to the true parameters, assuming that there are the true parameters of the distribution. So let's see how we can build the maximum likelihood solution. The likelihood, again, we need to express the likelihood for our dataset. The likelihood is what? As before, it's a function of the parameters, as in the Gaussian case, is the joint density for all the observations, including both samples and classes. Now, since all these are discrete values, rather than using a density, I can say that this is the joint probability of the values that I observed in my dataset. What does it mean? Let's go back to my training set. If I have white male, white female, orange female, black male, and black female, what is this? That's the probability of white, or better, x1 equal white, I rearrange it, c1 equal male, x2 equal white, c2 equal female, I will just use the initial for the colors, x3 equal orange, c3 equal female, etc., etc., etc. This is the likelihood given, the probability given the model parameters for the male and the female class. Now we assume that given model parameters, knowing the color of one cat will not tell us anything about the other cat. Once we know the probability is pi, those are the only value that we need to compute the probabilities for the other cats, which means that this product here factorizes, the likelihood here factorizes over classes. Which we can write as probability of x1 white class 1 male times, of course, given the parameters pi, times the probability of x2 white c2 female given the parameters pi, times the probability of x3 orange class 3 female given pi, of course, etc., etc., etc. Now, each of these is a joint probability for the feature and the class, and I can factorize this as a class conditional times a prior probability. So I can write this as a product of probability that I have xi given the class times probability of the class, which corresponds in this case probability that the first feature is white, assuming that it's male, times probability that is male, times probability that the second is white, given that class 2 is female, times the probability that class 2 is female, times probability that x3 is orange, given that class 3 is female, times the probability that class 3 is female, and so on. Now, we already observed that, well, we do it in the log likelihood. Here you have the same with a larger data set. It's exactly what I was writing before. Our likelihood is the product of the terms that corresponds to what I observed in my data set. Now, since we will need this later, we associate to each of, when we need to give values to the different features, we will use values 1 to k to encode the feature values. So, for example, in our case, white, black, orange. If we need numerical values, then we can't just stay with the labels. We will use 1, 2, and 3 to represent the features. So when a cat is white, we will actually say x1 equal 1. Remember that if this is a random variable gives me a value on the real line. We wrote x1 equal orange, but it doesn't make sense mathematically because x1 is not defined. A random variable is not defined over the set white, black, orange, but it's defined over numbers. So when we actually need, up to the moment, we just use labels as if they were numbers. If we need the actual value of the corresponding feature, we'll measure from, we'll count starting from 1. While for classes, we will assume that one class is 1 and the other class is 0. Now I don't remember which one I was using as 1. When we need, we will assign one class 1 and the other 0. Here we actually don't need it, so we can leave it undefined because but know that if we need, one label will be called 1 and the other will be called 0 when needed. Otherwise, we just leave M and F knowing that one of the M of the two is 1 and the other is 0. Now, this is the likelihood. So now when I write this, you can imagine that what I'm writing here is actually x equal 1 or x equal 2. Black becomes a symbol for 2, while male becomes a symbol for class 1. Now, as usual, our goal is to maximize the likelihood. Notice that the likelihood is defined in terms of the parameters. These are probabilities that are defined in terms of our model. Our model says that this is pi bm. This is pi om. So I can write all these class conditions in terms of the model parameter by simply replacing them with the parameter that gives me exactly that probability that I'm trying to compute. So for example, for these lines, I would have, and let me rearrange it. So I put all these terms before and then the priors. This will be pi b male times pi orange male times pi black female times whatever is in these dots times pi, here we have an extra color, let's call it C, male. Then I have times prior probability of male, the first one, times prior probability of male, times prior probability of female, and so on. Now, these prior probabilities are prior that do not depend on my parameters, so their actual value is irrelevant. Our goal, as usual, is maximizing the likelihood with respect to the parameters. These terms do not depend on the parameters. They are a constant that multiplies our likelihood, so we don't care what their value is. Whatever is the value is irrelevant. When we do inference, this will be the application priors. When we make estimation of the model parameters, we don't really care. The priors do not affect our solution. So the priors are irrelevant at training stage in this case. So our function to optimize is the multiplication of these terms. This is a function of the parameters pi. We want to find the parameters pi that maximize this function. As usual, we don't work directly with the likelihood, but it's easier to express everything in terms of log likelihood. Sorry. Don't work with the likelihood, but we use the log of the likelihood because that's easier to manipulate. So we take logarithm of this expression. The product becomes a sum. Here we split each class conditional into log of each joint into log of the class conditional plus log of the corresponding prior. These priors are constant. We said they are irrelevant. So we add all them together. What we get is an expression like this. This constant here is nothing else than the sum of the prior probabilities of the observed labels of my data set. As we said, we don't care about this because this does not depend on the parameters pi. This one depends on pi, so this one is relevant for our maximization problem. The other part is not relevant because it does not depend on the parameters. As we did before, we rewrite in place of these terms the corresponding value for the parameters. We said that if we have black male, black female, orange male, orange female, and white male, now I'm not sure that I'm using the same, I think it was white male, and orange female, then the log likelihood will look like what? It will be a sum of log pi bm plus log pi bf plus log pi white f plus log pi white m plus log pi o n or f. The sum of the probability of orange given female, white given male, white given female, black given female, and black given male. Now, these are sum over samples. I rearrange these terms in a way to put in the sum first all the terms of the male class and then all the terms of the female class, or vice versa, as you prefer. But in any case, I arrange them as to put together the terms that belong to the same class. So, for example, I rearrange so that I write log black female, log pi black female, plus log pi white female, plus log pi orange female, this is a first sum, plus a second sum, pi log black male, plus log pi w male. This is what I'm doing in this passage. This becomes a sum over classes of a sum of over the samples of that class of what? Log probability of pi ci xi. But since inside the sum ci is always equal to the class, I can drop the class. So you see the first sum always involves, and sorry, on the slides is the class comes before and the feature comes after, but it doesn't change. All the female parameters are in the first sum, and all the male parameters are in the second iteration of the outer sum. So the second sum always refers to a single class. So we can express, as we did with the multivariate Gaussian classifier, this as a sum over classes of these terms. Notice that each summation here depends only on the parameter vector of a single class. That was the same that happened with the multivariate Gaussian classifier. With the MVG, we had that since each class has its own set of parameters, the log likelihood can be expressed as a sum of log likelihoods that each refer to a different class, and each of these depends only on the parameter of the corresponding class. So the parameters of the male will influence only the summation when this is male. The parameters of female will influence only the terms where this LC refers to the female class. Which means that if I have to maximize this expression with respect to the parameters of a class, I can independently maximize the contribution given by the female class and then the contribution given by the male class. These two contributions depend on different set of parameters, so I can optimize them independently. Notice that inside each class, I need to consider the fact that the parameters of the class are tied, in which way they must sum up to 1, so they are not independent. But the parameters of one class can be estimated independently from the parameters of the other class. So we can concentrate on estimating the parameters of a single class at each time. We don't need to estimate them jointly. That's why? That's because, again, each class has its own set of parameters that are independent from the parameters of the other classes. The same that happened in the MVG. We see, for example, with the tied Gaussian model that this is not always the case. We can have models where this does not apply. Here, our choice of having different parameters per class allows us to, again, exploit that the maximum likelihood can be obtained by independently maximizing the likelihoods for the samples of each class. So essentially, we are fitting what is called, we will see, a categorical model to each class independently. So for each class, we need to compute the parameters of that class that maximize the likelihood of the corresponding samples. Each class will be considered on its own. For a class, this is the expression that we want to maximize. This pi c in bold is the set of parameters for the class C. So for example, for the male class, pi f in bold will be pi f black, pi f orange, and pi f white, or pi white f if you want to write it as I did before. These are the set of parameters I will compute the log likelihood over the samples of that class only, and I will want to maximize the log likelihood. So for example, in this case, I need to find the maximum with respect to the female parameters of this expression. I need to find the values of the pi's that maximize this expression. I have 3 pi's here, and I have a sum of 3 samples. I need to find the values that maximize the expression. The maximization of this expression, we can rewrite the expression in yet another way that will give us a way to compute the expression. How? Well, let's now consider a single class. A single class, and now let me do it a bit larger. So imagine these are all females, so I will not write the label again because we're considering the samples of one class. For example, C equal female. Then imagine that rather than having just the 3 samples that I have before, I actually have many more samples. I was using 3 before because it was short to write, but in reality, I will have many samples. In the slides, you have 10 to make it work. So what is my log likelihood? For the female class, and again, I don't write here the class female, but we should assume that we are doing it for the female class. My sum over samples will be what? I will have logarithm of pi for black, plus logarithm of pi for white, plus logarithm of pi for black again, plus logarithm of pi for black, plus log pi orange, plus log pi white, plus log pi orange again, plus log pi white once more. So each sample will contribute with a pi that corresponds to the value of the feature of the corresponding sample, to my log likelihood. Which I can rewrite, rather than summing over pi's, I can consider the possible values of the features. If I have 3 black cats, then log pi b will appear 3 times. If I have 3 white cats, then log pi white will also appear 3 times. Then I have 2 orange, log pi orange will appear 2 times. If I take this and I check how many times each time appears, that's the number of times that the feature appears in the dataset. So I can rewrite this as a sum over the possible values of the features, the number of times that features appears in the dataset, times the logarithm of the corresponding parameter that describes the probability of that feature given the class. And now I have to maximize this with respect to the pi j, or pi class j, if you want to put the class. In this case, we have a constraint. We have to optimize the expression subject to the fact that the sum of the pi j's, and here in the slides we also drop the class index, but again, if we are doing it for a class, we are considering this as the parameter of the class, but in the following we don't need to remember it's done for a class. We have to optimize this expression subject to the fact that the pi's must add up to 1. Now, in this case, unfortunately, we cannot just take the derivatives and set it equal to 0 because they would give us a solution that does not meet our constraints. So we can't use the trick that we used before to solve the problem. A possibility here that you have on the slide is to use Lagrange multipliers, which essentially means that we build an extended function which includes this constraint as additional terms multiplied by a Lagrange multiplier lambda, and then to solve the problem we just need to derive and set the derivatives of this extended function with respect to the model parameters and with respect to the multiplier lambda, both equal to 0. I will not explain why, but if you do this and go through the derivations, what you will obtain is exactly that the value that maximizes that expression under the constraint is to set each pi equal to the fraction of times that feature appears. Now, if this is the parameter of, for a class, for example, there would be probability of black given female, this will be number of black in the female class divided number of samples in the female class. So exactly the frequency of that feature inside that class, the results that we said before. And again, this comes from a maximum likelihood approach. Why we did the whole derivation if the result is intuitive? Because we said the result is intuitive when we use a maximum likelihood approach in the frequencies, with the frequencies approach to estimate the bounded parameters. Sometimes, often this is not enough, and then we would need to go through similar frameworks that we don't have time to see, but similar frameworks that will give us different solutions that in that case do not correspond anymore to just the frequency of the samples. This is just a very simplified version of what you would do with more complex models. So our solution is to use the frequency of the features in each class as our estimate for the parameters. For example, with the values that you have on the slides, this will be the estimate for the female class and this for the white male class. You can already see that there are some issues. I have few samples, so there are some zeros. These zeros would tell us that according to the model, there is a 0 probability that I have an orange cat given that it's female. This is probably not true. That's probably just because I have few samples in my dataset. That's the same as when we were doing the coin tosses. We said we observe 3 heads. Does that mean that we cannot ever observe tail? That's not true. Here it's the same. We have 5 cats. We never observed an orange female. Does this tell us that the orange fur cannot appear for any female cat? Probably not. But that's the best we can do with the tools that we have analyzed up to now. Okay, let's stop here, make break now, 15 minutes, let's make. Okay, so we have seen how to solve the problem for tasks where we have a single feature. Then we already said how to perform inference before. Once we have computed these probabilities, we already have everything we need to infer the class for a new sample. A new sample will be just a color of the fur of the new cat. Now, we may want to extend the model to more than one categorical attribute. So, for example, at the moment we will consider the color of the fur. Then we can imagine, let's extend and consider, for example, also the color of the eye. That's another discrete feature. It can have only a finite number of values. For example, for the fur, we have said there will be white, blue, black, and orange. For the eye color, we may say that it's, for example, yellow and blue, and green. Let's make 3. So, in this case, our feature vector, each sample will have a fur color, for example, white, and an eye color, for example, green. Now, we need to define a model, again, that gives us class conditional densities. So it needs to be able to compute what's the probability that I observe white fur and green eye given the female. And I need to be able to compute a value for all possible combinations. What are the possible inputs for my likelihood function? What are the possible values of my feature vector? There are all the combinations of the fur color and the corresponding eye color. For each of these combinations, I need to be able to compute what's the probability of the corresponding sample. So if I look it into 2D dimension, I have fur, I have eye color. I will have 3 values for the fur, 3 values for the eye color. My possible samples will be all the possible combinations of these two. Now, how can I extend the model to consider combination of two features? So in this case, fur color and eye color. Well, one possible extension is, we do the same as we did for the previous task. These are the 9 values that my feature vectors can take. I give a probability for each of these combinations. So I assign probability of white and yellow given the class female. This will give me probability of white and yellow given female. In terms of a feature vector, it will be the probability of the vector white and yellow given female. But we can just write it in this way. Probability that the cat is white and has yellow color. Then I will have, let's say this is the fur, white, black, and orange, yellow, blue, and green. Then I will have this term I will represent it with a parameter pi yb that tells me the probability that the cat is black and has yellow eyes. Then I will have one parameter that tells me what is the probability that the cat is orange and has yellow eyes. So essentially, for every combination, I treat it as if it was, well, I can treat it as a combination for which I give the joint probability, or if you want, I can also interpret the model as having a single feature that is the tuple fur color and eye color. It's the same. The input space is exactly the same. All possible combinations of fur and eye color. Then, with the first interpretation, I need to specify a parameter for any combination. With the second interpretation, I'm just creating a new categorical task where the feature values are the Cartesian product of the feature values for the two original features. In any case, this requires that for each combination of the fur and the eye, I specify for each class what's the probability of the corresponding fur and eye color for all possible combinations. Now you see that before I had 3 parameters for the fur. Now if I have 3 values for the fur and 3 values for the eye color, this means that my model will have 9 possible combinations. So I need to specify 9 possible parameters. If I add another categorical variable, let's say, well, it's difficult to figure out a different categorical variable. Let's say that I have the tail length, but not measured in centimeters, just measured as short or long. So I have categorical feature that tells me it's a short-tailed cat or is a long-tailed cat. Somebody defines how to measure this and just tells me this feature. Then I need to take this 9 and multiply by 2. So now I need 18 parameters. If I have an additional feature, let's call it f, which has values in a set, S, and the cardinality of S is this, then I will multiply my previous feature by these values. So if I have n features, f1, f2, f3, and so on, for example, fur, eye, tail length, each of these takes values in a set S, then the number of combinations that I need to consider is the product of the size of each set. So it grows exponentially as I keep adding features. So it's not something that I can do if I have more than 2, 3, maybe 4 features, because it becomes soon I will have too many parameters with respect to the vectors that I have. That means that for most of these combinations, I will actually not even have samples in my dataset because my dataset is limited. So some combinations will not have samples at all. We have seen that not having samples causes problem because that means that we will estimate that combination can never happen. But that's probably just because that's rare enough that when I consider all combinations, if my training set is limited, I will not be able to have samples of all combinations, even if they exist. One possible approach is to resort to the naive Bayes approximation again. Naive Bayes says what? Says if I have multiple features in my dataset, I assume that the components, the features, are independent. So for example, I assume that the fur color is independent from the eye color, which means that whatever is the combination fur eye, the probability of, for example, white and yellow, given the class, of course, this is always independent given the class, can be factorized as the probability of white given female times the probability of yellow given female. Which means that now I just need to specify the probability of white given female and the probability of yellow given female. So for example, if I have three colors, white, black, and orange, I will have probability of white, probability of black, and probability of orange, again, for a single class. And then if I have yellow eyes, green eyes, and blue eyes, I will have pi y, pi g, and pi blue. Let's call it blue to distinguish from black. Let's call this K for black and this B for blue. Which means that if I have a cat that is white and yellow, the probability of white and yellow given female will be pi white times pi yellow. Now I have, again, one parameter for each feature that I can observe. So in this case, I have 3 parameters for the color and 3 parameters for the fur and 3 parameters for the eye. Number of parameters is 6. If I had another category, tail, long, and short, and I assume it's also independent, I will have pi short and pi long, additionally 2 parameters. So what was before a product of the size of each, of the set of the size of the domain of each feature, now becomes, in terms of the number of parameters, a sum over the size. If my feature 1 has cardinality, the set of feature 1 has cardinality S1, set of feature 2 has cardinality of S2, and the same for S3, the number of parameters is the sum of these. What do I lose? I lose that I ignore possible correlations. I assume independence, so correlations become 0. Maybe if a cat is orange and female, then it will have yellow eyes, because the two things are correlated. My model will ignore that correlation, so we will not build, if this is true, it will not build a good model for cats that have both orange fur and yellow eyes, because it assumes independence, so it assumes that these two factors are not related. If they are related, then my model, as was for the Gaussian model, is not taking correctly into account correlations. Here it's more difficult to see, but we have seen what does it mean with the Gaussian model. When we ignore correlations, we see that we fit a model that may not give us a good estimate for the density for those cases, for samples that should be considered correlated, because my model does not consider their correlations. Indeed, for any combination, if it's white, here I will always multiply by pi white. Now, this has the benefit, on the other hand, that the number of parameters is much smaller. So we can now fit independently the parameters pi to each feature vector, to each feature component for each class, and then we'll just need to multiply the corresponding parameters for the combination of features that we have for our test sample. For example, if we have a yellow cat, probability of a yellow eyes and white cat, it will be probability of white, yellow given female, and then the other I will need to compute probability of white, yellow given male. This will be just pi y male times pi white male, sorry, female here, and below it will be pi white male times pi yellow male times pi white male. Then I will multiply this by the prior, and this is proportional to the posterior that I need to compute. So I solved my problem. Or if I want, I just compute the log-likelihood ratio between these two. So I compute log pi YF. Oh, okay, we will see it later. So we can make inference, and in this case, when we need to compute the class conditional likelihood for our test, we will use the product over the features of the parameters that describe each feature independently. Okay, questions up to here? Of course, we can use naive Bayes also when we need to combine discrete and continuous random variable. For example, we have full color and then the length of the tail in centimeters. We can make a Gaussian model for the length of the tail, and then this is called categorical model for the full color. And then assume that they are independent. The product, we will just need to independently fit the Gaussian to the length of the tail, the categorical to the full color, and then when we compute the class conditional likelihoods, the class conditional likelihoods for a cat that has, for example, white color and, let's say, 20 centimeter tail, it will be what? The density for 20 centimeter tails, assuming the class, times the probability of white given the class. This will be a categorical model. This, for example, may be a Gaussian model that I estimated for the tail length. So we just need to combine the models. Maybe we will see, if we have time, we will see an example at the end. Now, before we move to this, let's now go back to the categorical model and see how this can be extended to create models, for example, for tasks where we need to manipulate more complex structures, for example, text. This will give us an example of how to extend these models, and will also allow us to see an equivalent model, and then we will use this model for the next laboratory. Now imagine that, for example, for the moment we have seen how to use the categorical model to describe, for example, the fur color of a cat. Now imagine that I want to do something similar, but this time I have, well, not that similar. We will see that it's similar, but it doesn't look similar. Consider a problem where I have some piece of text. So, for example, one line of text, and I want to identify some property of this text. For example, imagine this line of text is a newspaper article. I want to identify the topic of the article. Or I have a text in some language. I want to identify the language. If you use Google Translate, you have automatically identified the language. I have the text. I want to understand in which language the text is written. Or, as I said, typical example, I have some text that talks about something. I want to label it with a topic. So, for example, this is a paper about politics. This is a paper about economy. This is about some gossip or things like that. Now, in this case, we deal with discrete objects. The texts are made of words. Words are not continuous values. Words are discrete values. So we can model the text as a sequence of discrete values. Before we had a categorical model where we had a single feature inside our data. Now we have samples that are not same dimensional anymore, but whose size depends on the length of the text, and the length of the text essentially depends on the words that are inside the text. How can we model this kind of object? We'll model it as a sequence of tokens. Each token will be assumed to be a random variable that represents the word. So each word will be represented in terms of a random variable xi. Xi can take a value in all the possible words for that language or for that topic. So we will have a set that contains all possible words, the dictionary that represents the possible word that can appear in our document. And each word of my document will be represented as a token that can take one of these values. Now, the problem is how we can model the probability of, for example, a topic or the probability of a language given the text. For example, let's imagine we are doing topic, or no, let's make languages maybe easier. This is an English utterance. We want to label it as English. So we need to compute probability that the language, which for our case is the class, probability that the class is English, given that our document, now let's call this sequence Y, given that the sequence Y is the sequence how are you. This is the kind of things that I want to compute. Now, if it's a closed set identification, then I will have other possible competing hypotheses. The one that I know my language belongs to, my sentence belongs to, for example, the set of all languages that I have in the world, which is, if we restrict ourselves to official languages, is not that large in any case, few, something more than 100, some hundred, I think 100 something. That's not really important. In any case, it's a closed set. I will test it against all the languages that I have in my task. We are assuming a closed set, so I know that it's one of the languages that I want to recognize. We don't consider the case when it can be another language, because that would make things slightly more complex, but at this point it's not necessary. What I need to be able to do is to answer to this kind of problem. What we'll see is that we can do it in a similar way to the categorical model that we analyzed before. How do we solve this? Again, with a generative model, we need to be able to compute the probability of the sequence that we observe given the language that we assume. Once we have this, if we are able to compute this for all languages, we have everything we need to perform inference. This is, again, the class conditional likelihood. Given a value for our input, now it's not a feature vector because this can have a different size. The size of Y depends on the number of words in the document. So it's a variable size. So I will not use the word feature vector in this case, but given our input document, the document that we want to classify, it will be represented as a sequence of tokens. We need to, if we are able to compute this probability, and now it's a probability again because these are discrete, so it's a probability. If I am able to compute this probability for all classes, then probability of class equal English given Y will be what? Probability of Y given Eng times prior probability of English divided the marginal for Y. But I hope we understood now that we don't really care what's the value of the marginal, because if we want, once we have computed all joint, we can always compute it, but in any case, we won't need it when we want to do the class assignment, because it will not affect what is the class that has maximum probability. So for example, for French, I will have pi of Y given French times prior probability of French. Again, divided the marginal, but the marginal is irrelevant. So once I am able to compute these terms for all languages, I have solved my inference problem. The problem now is the real problem is how do I model this? Now, how do I model this will tell me how I describe the distribution of the words inside a document. Now this is a bit more complex, so we will just consider a very simple model, and then we will try to extend it in a simple way, so we will not for sure consider the models that you have, the models that are able to produce documents that may look like real documents. So the models that we will see are very simple and very crude, but they have the same underlying idea of what you would have for generative models that you use to generate text. So the underlying idea is the same, being able to model the distribution of the words in a document. Now here we do it for classification, so we do it in a way that is geared towards classification, and in a way that is fairly simple because we can treat it with a simple machine, and it's actually a matter of doing few computations. Then these models were used up to a few years ago. Now they are not that used much anymore, but they are a good starting point because the overall ideas are not that far. Now, in our simple model, we have that a document is a simple sequence of words. And we said, let's treat this sequence of words as random variables that represent the words that appear in the document. We start making an assumption that is very inaccurate, but simplifies things a lot. We assume that all these random variables, given the topic, of course, are independent. And they are identically distributed. What does it mean? It means that if I write a sentence like this, the fact that here I have the word are does not depend, the probability that the second word is are does not depend on what is the first word. Now it's clear that this is not an accurate model. This means that I could write things like I don't know, things like, okay, now this doesn't even make sense. A sentence like this makes perfect sense. It's the same probability that if I write, or let's not use that example. Let's use a different example. A sentence like this is plausible according to my model. A sentence like this, according to my model, has the same probability as the first one. Because if we assume that the words are independent and they do not depend on the previous or the sequence or the subsequent words, we can show that the probability of a sequence does not depend on the position that a word has in the sequence, but just depends on the individual words that make up my sequence. Why? If this is independent, the probability of the sequence x1, x2, and x3 is the product of probability of x1 times probability of x2 times probability of x3. Of course, remember that here is given the class. But this is also the probability of the sequence x3, x2, x1. So any sequence has the same probability if it contains the same words. This is, of course, not true. But we see that taking into account correlations, so the words are not independent, there are strong correlations. Which word comes after depends on what was before. But accounting for these correlations makes the model much more complex. So for the moment, we are happy with a model that is inaccurate, but we will see for some tasks it will be accurate enough. It will be accurate enough to prove something in our next laboratory, and it's also easy to work with. Well, easy with respect to other possibilities. So if we have this, we have said that once we have a sequence of words, a document, the probability of the document given the class will be the product of the probabilities of the individual words. So now we shift the problem to modeling the probability of individual words. This is a model assumption. We still need to define how we compute these terms. How do we compute these terms? What's each xi? xi is a categorical variable that can take a value in my dictionary. So it's a single feature that can take one out of k possible values where k is the dictionary size. That's the same as the fur color. The fur color was a categorical variable, a value that could take, a random variable that could take a value between among a discrete set of possibilities. It's the same, just the size of the possibilities is probably much larger. Here we have few thousand words. But we can, as first approximation, assume that we can build the model how? By simply specifying for each class what's the probability that we observe the token xi. So for each word that can appear in my dictionary, I say what's the probability that I observe A given that it's English. The probability that I observe an given that it's English. Now, of course, if this is a language recognition task, this is not the dictionary of a language. This is the dictionary of all the words that can appear in all the languages that I consider. So when I say dictionary here, don't focus on the dictionary of a language. The dictionary is the set of all possible words that can appear in my task. If it's a language recognition task, I can have English sentences, I can have Italian sentences, then my dictionary is the set of all the possible words for all the possible languages. Then, what I will have, that for example, probability of how given English will be large, while probability of how given Italian will probably be something that is very small, because we don't see the word how in Italian. Probability of A, well, that's not very different, because A is used in English, a cat, A is used in Italian. It's a preposition. I go home, I say, vado a casa. It's used in a different way, but still, the word A appears in both languages. And we already can start to imagine that if a word appears in both languages, that's not very useful to tell what is the language of the text. It's not a discriminant word. In any case, I will have my dictionary, and my model defines, as we did for the fur cat, for every possible word, the probability of the word given the corresponding class, the corresponding language. So I will have, for example, if I have a dictionary with 20,000 words, I will have 20,000 parameters per each class. Once I have the set of all these parameters, if I have somebody gives me the values for these parameters, I can use these values to perform inference. For example, for the sequence of words, how are you, I will have that the probability will be pi of the word how in English. Let's imagine I'm testing the sentence with respect to the English class. Then I will be pi how English times pi of word are, given that it's English, times pi of word they in English. So for each language, I will have a set of parameters for all the words, and this corresponds to the probability of the word how, given that the class is English, the probability of the word are, given English, and so on. Is it clear up to here? So this is the model. This is the full model. We still miss what? How we compute these values pi ci. How do we compute the values pi ci? Well, we will need to take some label dataset, build our log likelihood for the documents in that dataset, maximize the log likelihood with respect to the model parameters, and that would give us the values for the parameters pi. Imagine, for example, and I will do it quickly, that we have, I will already assume, since we have different parameters for each class, we already know that our likelihood will factorize over classes, so we can independently estimate the parameters of each class. This is the same we did before. Before we didn't do any assumption on the structure of the likelihood before we got to that point, so that point will hold. I will not prove it again, also here. So now imagine that I have English documents, and I have a set of English documents, Y1, Y2, Y3, and so on. My likelihood is what? Well, it's the product over documents of the probability of the document given the class, times the prior for the class, but again, this prior, we will ignore it because it doesn't depend on the model parameters. Each of these can be computed how? If Y1 contains the words X1, 1, X1, X2, 1, X3, 1, so this one here is the document, this will be a product over documents or a product over the words in the document, call it J, of pi x j I. So this is the i's, the j's word in document I. Notice that I can simplify all these processes saying that I collect all my documents in the document Y that contains the sequence of words for the first document, then the sequence of words for the second document, and so on. So I put all my words in a single document. Then if I were to compute the likelihood for this large document that collects all the words, I would get exactly the same expression. So actually what I get is that the likelihood is a product over all the words in all my documents. Remember that the sequence of the documents doesn't matter, of the probability of the word that I have observed. Which means in the log likelihood, I will have a sum over documents and the sum over the words of a document. But again, this I can see it as a sum in a set. This is the number of documents, let's call it M. In a set big N, which is a new document that collects all the words that I have in my training set for English, of the log probability of the words that I observed given English. This is what, again, I can see the model as if I have a collection of n categorical random variables, each one taking a value in my dictionary. So each of these, I can see it as a sum over all the words in all the documents of the log probability computed for each word in the document. But each of these is what? Well, if xi is the word A, I will have pi A English. So each of these terms is logarithm of pi xi plus English. Now, these terms looks what? If you remember what we did before the break, it looks very similar to the likelihood that we had for the full color. Actually, let me rewrite in this way. Let's imagine that I have a document where A appears 3 times, R appears 2 times, they appears 5 times, and so on. What is this sum over all the words? Well, I can transform this sum over sum over the words in my dictionary of what? If A appears 2 times, I will have the logarithm of pi A 2 times. So each word will appear nj times. My log likelihood is a sum over words of the log probability of A over that word given English times the number of times that I see that word. For example, here if I have 3 times A, I will have 3 times in this summation log of pi A English. Here I will have log of pi English 3 times. Okay? That's the same we did with the full color. We are actually doing the same model. Just our training set now is the set of all words in my document. So if you see the problem, we are actually solving the same problem we solved for the full color of the cat. This time, the dictionary is the set of possible values, and the samples are not really the documents, but the set of all the words inside my documents. If I see the problem as I put together all the words that I have in the documents that represent a given class, then I'm building a likelihood model I'm building a categorical model for the words of that class. And the model is the same model we did for the full color. Then it shouldn't be surprising that the maximum likely solution will be the probability of A for English will be the number of times I see A in English words divided the number of English words that I have in my training set. When I need to optimize this with respect to the pies, this has the same expression as the categorical model we were using for the full color. That's exactly the same model. Just now, here the NJs are not the number of times I see color yellow or color orange, they are the number of times I see each word in my dataset. So the categorical model can be used to build a document classifier. What does it mean? Practically it means that what we will do is we take our document. From this document, we count each word, how many times it appears in the document. Then we transform this to frequencies of each word. And these frequencies will correspond to the probability of that word given the class. Maximum likelihood estimate. The maximum likelihood estimate is the probability, is the frequency of the word in the corresponding documents of the corresponding class pulled together. So we pull together all the documents of a class. Then when we have a sentence and we we have the sentence and we want to identify to which language it belongs, we'll compute the likelihood of the sentence a cat given English, then the probability of a cat given Italian, and so on. How? Well, as a product over the token. Also in this case, we factorize the probability of the whole document over its token. And the same for Italian. But these are what? Well, I go in my dictionary for each class. This will be pi I n, pi cat n, pi a Italian, and pi cat Italian. So the frequency of the word cat in Italian documents. And those are the numbers that I computed on my training set. And then this will give me class conditional likelihoods. I will actually work with the log typically of these terms, and then combine it with the priors. You can see that why I work with the log. Imagine that each of these sum up to 1. So all these are typically much smaller than 1. If I have a long document, I'm multiplying several terms, each of them much smaller than 1. When I get 1,000 words, I probably get a number that is 0 on my machine, but that's not 0. The probability is not 0. I will get very small number for both hypotheses, but one will be much larger than the other. If I were to compute the probabilities directly, I would saturate and underflow on my machine, I would get 0. If I work with the log, I will have log of pi 1, log of pi 2, and so on. All these terms will not saturate towards 0. So also in this case, we will rather work with logarithm of the probability. But that's a possible way to build the model. Now, on the slides, you have an alternative method that is also interesting because it shows us that it's the same actually method. An alternative method that is based on the consideration, okay, let's not consider just the sequence of words, but let's use what may look as a simplified model. We directly count the occurrences of each word inside the documents of that class. So for a document, we count how many times each word appears in the documents of that class. Then we represent a document y1 by the number, so we have a feature vector that contains a number of dimensions equal to the size of the dictionary. For each document, it will contain the number of occurrences of the word inside the document. Now, in this case, we have feature vectors. And we can model these feature vectors in terms of multinomial distributions. Now, here I will go quickly because we don't really care about the details. But if we were to repeat the whole procedure, we could say, okay, let's model y1 in terms of a multinomial distribution with some parameters pi. Remember that in a multinomial distribution, the parameters pi represent the probability of one occurrence of one token. So the parameters pi will give us what is the probability that I have one A, the probability that I have one N, and the probability that I have one Z. Then the multinomial distribution becomes a bit more complex because it says that the probability of a vector that represents counts is the probability of one of the sequences that can give me that count times the number of ways I can obtain that count with different sequences. So I will have that the probability of a vector of counts is the probability of a sequence that gives me that count times the number of sequences that give me those counts. For example, if I have A equal to 2 and cat equal to 1, I can have that generated from this sequence, I can have that generated from this sequence, I can have that generated from this sequence, and so on. So the second term is the probability of one of these sequences, and the first term, the multinomial coefficient, is the number of sequences that can give rise to those counts. Why am I introducing this? Because sometimes documents are, when you work with documents, typically this is the characterization that you have, that you had when we were using categorical models. Represent the documents not in terms of words, but in terms of occurrences of the words in each document. Now, this means that this is the expression for the class conditional likelihood. We have a multinomial coefficient, number of sequences that can give those counts, times the probability of a single sequence that can give those counts. But we observe that from the point of view of the model, only this part depends on the model parameters. This part does not. So even if it looks complex, we can already forget about the multinomial coefficient. Now, if we were to build the log likelihood model for this new task, we would have that given a document I for class CI, the likelihood for a document would be what? Would be this expression, the logarithm of this expression. This is what? Is the probability of word J in class C to the power number of times I observed class J. That's the multinomial distribution. If you don't remember the multinomial distribution, go back to the multinomial distribution. This represents the probability that I observe this amount of times the word xj, the word j, inside my document, inside my vector of occurrences. So I observe xj times the word j, and the word j has a probability of appearing pi cj. So for class C, it has a probability pi cj that a single word appears, the word j, and in my document it appears xj times. So this xj is actually my vector. Here I call it y because before the document was called y, but now this is a feature vector, so let's call it again x. My x contains the occurrences of the words. The probability of one document having these occurrences is computed in this way. For each word count, I take the probability of that word to the power the number of times that word appears. And everything is then multiplied by this coefficient. When I move to the log, it becomes what? It becomes a sum over the sample of that class of what? A sum over words of the number of occurrences of word j times the log probability for the word. So in this case, if I have 2 times the word A and 3 times the word they, this will be 2 times log P, C, P English, let's imagine the class is English, word A, plus 3 times log probability, actually we wrote it this way, A English, pi they, class English. So this feature vector now gives me directly the number of occurrences of each word. Of course, it will have occurrences for all words, which means that for the other words, the occurrence will be 0, so I'm not writing the corresponding terms in the sum. But this is what? Well, if we look at what we get for the log likelihood, if we call, this is the number of occurrences of the words inside a document. And then I'm summing over the documents in my class. Which means that if I have the first document where they appears twice, then and A appears 3 times, and how appears once, then the second document, A appears 0 times, they appears once, and how appears twice, and so on, all these sums of the documents becomes what? I will have log of pi A 3 times, 3 from the document 1, and then 0. It's a sum over the samples from document 2, plus log of pi, they English, how many times? Well, for the first document, I will have 2, and then for the second document, I will have 1, so overall 3. And then let's make this one as well. 2 times log of pi how English, which means that my log likelihood, also in the case of the multinomial model, will be what? A sum over dictionaries of the number of occurrences of the word in the dictionary times the log probability of having a single occurrence of that word. This is what? This is exactly the same likelihood as the categorical model. Exactly in which sense? It's the same likelihood up to some constant, but we know that the constant, which corresponds to the multinomial coefficient, is irrelevant for the maximization. The function that we maximize is the same as the one we were optimizing before when we introduced the categorical model. So the solution we already know, also in this case, is for the probability of observing a single word in a class, is the frequency of that word in a class. And notice that when we do inference, we also have the same solution, because when we do inference, when we compute for a given sentence the probability of x given the class, this coefficient does not depend on the class. So at inference times, it also disappears, which means that sometimes you will see the categorical model for documents expressed in terms of multinomial model. A multinomial model describes these documents in terms of number of occurrences of words inside the document, but this is exactly the same model that you would get if you were considering the documents as sequence of words, each independent of each other, each with its own probability that is the same, that depends only on the word that I observe. So typically you will see these models are called, the extension of these models are called n-gram models or multinomial models, but the multinomial models are exactly the same model as the categorical model that we have seen before, which is solved exactly the same way as the categorical model that we have seen at the beginning of the class. So it's just a matter of expressing the same thing in different ways. I'm introducing this because this is how you may find it expressed somewhere. It's the same model that we just discussed. It uses a different likelihood expression, but since this likelihood expression is just proportional to the likelihood of the categorical model, then that's something that is general. If we have two models where the likelihood of one model is proportional to the likelihood of the second model, these two models from the point of view of inference are the same. Because maximizing one with respect to the parameters is equivalent to maximizing the other. When we compute class conditional densities, they will be all scaled by the same constant that does not depend on the class, which means that also all the inference will be the same. Now let's use this model in practice. Well, before we use it in practice, let's see another good, interesting property of these models. Once we have trained our model, whether we use it, we represent it as a categorical or a multinomial, we have said it doesn't make any difference. In all cases, we can imagine we take our documents, we treat as a sequence of words, and then we compute the frequency of the words in each class. Then, when we have a test document, here it's called small x, before it was called small y, but let's say x is the text, small x is the test document, so how are you? We said we can compute posterior probabilities by computing probability of how given class 1 times probability of r given English again times probability of u given English. Now, if it's a binary problem, we can also, so from this, we multiply by the prior of English, and we get something that is proportional to the posterior. If it's a binary problem, as we did for the, so now imagine we have a binary problem, so we know it's either English or Italian, we can compute a log likelihood ratio, and then compare this with minus the prior log odds of the two classes. Notice that we have P of English plus P of Italian equal to 1 in this case. And it's a prior probability, so somebody needs to tell us, depending on the task, what is the prior probability. Now, if I have to write this in terms of the log densities, now let's, in terms of log of this, what do I have? The first will be log of pi how English plus log of pi r English plus log of pi u English. As before, let's not write it in terms of the sequence, but let's write it in terms of the dictionary occurrences. I will have, so imagine that I have a long sentence where how appears 2 times, they appears 3 times, and so on. This sum would be what? Well, if I have, for example, how are you okay? This is a longer sentence. Here, I would add the log of pi r again, then log of pi u English again, and then log of pi, okay. Now, rather than writing this as a sum over the words, let's write over the tokens, let's write it as a sum over the words. I have that log of pi how appears 2 times, then I have 2 times log of pi r, of course for English, and then I have 1 time log of pi u, 2 times, sorry, 1 for r, 2 times for log of pi u in English, and so on. So I can rewrite it as a sum over tokens over the dictionary of the number of times I see the word J in my dictionary, in my test sample, times the log probability of the corresponding word in the class. So I have a run over the whole dictionary. If that word does not appear, this will contribute 0. If the word appears 2 times, for example, R, here we'll have 2 times log probability of R in English. This is the term for the numerator, the English class, the same for the denominator. I can express it in this way. And then, if I express it in this way, I can see that if I have my document represented as occurrences, so rather than a sequence of words, I represent my document as number of R, number of A, number of R, number of whatever, number of they, number of ZZZ. So the number of occurrences in my test document of each word, I can express it as a linear function of this vector x. So if I, at test time, I use the multinomial, and in this case using the multinomial representation is more interesting, the multinomial representation of the model, so I represent each document as the number of occurrences of each word, then both the multinomial and categorical model, which are the same, will give me a log likelihood ratio that is a sum of the occurrence, a weighted sum of the occurrences of each word. And the weights will be what? For words I, it will be the log odds for that word inside the 2 classes. So the first term here, for example, would be log probability of A given English divided probability of A given Italian, as estimated from my model. So I will count the number of A's and multiply it by this term. Then I sum it for the number of R times the probability of R given English divided the probability of R given Italian. And this corresponds to a linear model in the vectors that correspond to the occurrences of the words. Then I will compare this with a threshold, and again, this corresponds to the expression of a linear model where the boundary corresponds to the solution x transpose b equal to the threshold. So again, this is a linear decision function. So a model that computes linear decisions. Now on the slides we have an example which is slightly different. The task is inferring the programming language that the script is written into. So we have some text file that we know contains some program. We want to identify what is the language that the program is written into. Now, we consider a simple model. We assume that the name of the variables, the name of the functions, and at first approximation also the keywords are not relevant for the task. We concentrate only, just to make it manageable in the slide, on the punctuation characters. And in particular, we consider sequence of words, the sequence, open or close curly brackets. This will be considered as a single element. So either open or close will be the same symbol for us. So it will be curly brackets, square brackets, round brackets, colon, semicolon, dot, and comma. We know that in the two languages, these punctuation marks are used in a different way. For example, curly brackets are much more prevalent in C code than in Python. While, for example, the dot is probably more something that you find, or the colons is something that you find more in Python programs than in C. So let's see how we can build a model for this. Now, these are values taken from very simple scripts, so short scripts, but if I remember right, this should be real values. You have training set that consists of 4 C scripts and 3 Python scripts. Now, depending on whether you use the categorical or multinomial model, they will be represented differently. Here we use the multinomial representation, but we said the model is the same. The multinomial representation, we count for each document the number of occurrences of each symbol. But what we need for inference is just the total number of occurrences in each document. So we can either take each document, count the symbols, and then use this as feature vector and sum them, or go back to our 4 scripts, treat them as if they were a single long script. In this single long script, compute the number of occurrences of each token. It will give the same answer. The number of occurrences, this is what you have below, is the number of occurrences of each token. What changes is just the interpretation that you give to the feature vectors. But we have seen that these two interpretations are equivalent, so we will switch to the one that is more beneficial according to what we're doing in that moment, but we know we are doing the same thing. So for the moment, we know that for inference, we need to compute the total number of occurrences of each token in the documents, so we do that. We do the same for Python scripts. These are the occurrences of each word, of each symbol inside C scripts and inside Python scripts. Maximum likelihood estimate, each symbol is represented in the class by the corresponding frequency. So we take these values, we compute their sum will be the number of C symbols. Here the sum will be the number of Python. Then we will take the C symbols and divide by the total numbers. So in this case, 30 plus 46 plus whatever. And this will give the frequency of curly brackets in C scripts, the frequency of square brackets in C scripts. We repeat for Python, we get these values. These are the frequency of curly brackets inside C scripts. This is the frequency of curly brackets inside Python script. We already see that there are more it's more likely for a curly bracket to observe a curly bracket in C script than it is in Python script. It's more likely to see colons in Python script than it is in C scripts. It's more or less the same for round brackets. Round brackets represent function calls in both environments. In Python, they also represent tuples, but we don't use tuples that much. So it may make sense that more or less the amount of tokens square bracket is similar in the two scripts. Now, when we want to make inference, we now need to compute our class posterior, and since it's binary, we don't go through the class posterior explicitly, we do the inference through the log-likelihood ratio. Why? Because we will see that that tells us something on which of these is actually interesting to distinguish the two classes. The log-likelihood ratio is what? Well, I have a script X that I want to classify. I can either do what? Well, for each word in the script, compute the corresponding log pi probability, as in the categorical model. So my script, let's say that it has first a round bracket, then a curly bracket, then a square bracket, then again a round bracket, then colons. I will do, for the English, my log-likelihood ratio will be what? Will be log of pi for C for the round brackets, times pi of C for the curly, times pi C for the square, and so on. And below I will have the same computer for Python. So if I want, I can see as log pi C round divided by pi round plus log of pi C curly divided by Python curly, and so on for each token. Or I can represent this sum over token over the elements of my script as a sum over token. So I will have 2 times logarithm of pi C round bracket divided by Python round bracket. Then I will have 1 logarithm for the curly brackets in C divided the curly brackets in Python, and so on. So for each token, I see how many times it appears, and then I add at times log odds for the corresponding token that number of times. So here I have a sum over the words in my document. Here I have a sum over the words in the dictionary, as we did before. If I use the second representation, I can represent my document in terms of the occurrences of each symbol. So, for example, my test document will be represented as one of these lines, the number of occurrences of each token in that document. Of course, it may have different values, but those will be the values for the C script. And then I can represent my log-likelihood ratio as a product of what? Number of occurrences of each word times the log odd of the corresponding word. The log odd of the corresponding words, I can pre-compute them. It's the log probability of C curly brackets over pi curly brackets. So curly brackets for C divided curly brackets for Python, then I take the log. So it's the log of this divided by this. Then I do the same for these two, then the same for these two, and so on. These are the values that I obtain. Now, if I have a document which has 2 curly brackets, 4 square brackets, 1 round brackets, and 3 columns, my score, my log-likelihood ratio will be 0.837 times 2 plus 0.165 times 4 minus 0.052 times 1 plus minus 3 times 1.754. And then if I don't have the others, the other will be 0 times the corresponding plus 0 plus 0. So they just do not appear. This will be my log-likelihood ratio. Notice that then my decision threshold is my decision is log-likelihood ratio compared with the threshold. But the log-likelihood ratio already tells us something. Even if we don't know the threshold, the higher the log-likelihood ratio, the higher our support towards the C class. The lower the log-likelihood ratio, the more negative it is, the higher our support for the Python class. Then whether we really decide for C or Python depends on our prior belief that this is a C script or not. For example, we may have a strong support for C, but we know that this is an exam for the first year, so we know that the prior probability that the student did it in C is very, very small. So even if the prior support for C is large, we may still decide that it's not large enough with respect to the prior probability that is Python code. But in any case, the higher this is, the higher the strength of our evidence towards the C class. We can see that we add positive values whenever we see curly brackets. Whenever we see round brackets, we add small negative values. For colon, we add large negative values. For semicolon, we add large positive values. What does it tell us? It tells us that these are discriminant characters. Whenever we see one character of this kind, that is strong evidence for the curly brackets towards the C class. For the semicolon, even higher towards the C class. If we see one semicolon, this is strong evidence towards C. Python doesn't use really semicolon a lot, so the evidence is strong with respect to the C class. If we have colons, the evidence is strong towards the Python class. Colon in C is much less used. So if we see a colon, there is a strong support towards the fact that this may be a Python script. So the values of the coefficient that we have here represent our supports towards one hypothesis rather than the other. We can also see that there are symbols which are very discriminant. If we see them, that's a strong support for one class. Symbols like the square bracket are less discriminant. There is not that strong support towards one class. They have more or less the same likelihood inside both classes, so seeing a square bracket doesn't tell us much on the script. We need to see. It tells us something towards the Python, but the support is weak. Or if these were real scripts, this would be even smaller. But for example, if you have two scripts like this, then you can compute log likelihood ratio, and you would end up saying that the first script has a log likelihood ratio that favors the C class, the second has a log likelihood ratio that favors the Python class. Of course, the final decision will be based on the prior log odds. So if the prior log odds for the two classes are the same, I would say the first is C and the second is Python. Of course, this depends on the prior probability, as we said before. Okay, we're good. Few more words and then we're done, because the last set of slides I already told them before. Some issues of this problem: if we have words that are rare, this is a problem. If a word can appear in a topic or in a language, now here we use word topic, but the topic is the same as the language. If you want to do topic recognition, it's similar. Just in this case, the dictionary of words will be the words that can appear in different articles, and then the topic will be the class rather than the language, but there is nothing different. For example, in politics, we may see a lot of words that represent political parties and so on. In sports, you will see words that represent, for example, the football or the field and so on. So there are words that allow us, that are more frequent in some documents of a topic rather than in the other, and it will do the same kind of process. Problem: if we have a word that does not appear at all in a topic, then our maximum likelihood will say that the probability of that word given the topic or given the class is 0. That's the same as the head tossing problem, where we had few heads and we said the probability of tail is 0. If a test sample contains the word, then the probability of that class for the sample will be 0, assuming that the word appears in the other classes. Even worse, if we have more than one class, well, okay, let's keep this aside, we'll say it in the lab. In any case, if the word appears only in one document, then whenever we see that word, we will say that that document belongs to that class. And there is no chance we will change our idea regardless of the other words. And now this may be a crude approximation. A way to mitigate this is to, we see this better in the laboratory because we will explain how to do it, is to introduce models that take into account, well, they are approximation of the Bayesian models. We will not see them in details. We'll see an approximation without showing that it's really is an approximation, where essentially we will augment our documents by assuming that each word appears in each class at least a small number of times. We will discuss this better when we see next laboratory, when we will use this, and then I will explain why we do this. Essentially, we will avoid the problem of frequency estimates being equal to 0 by saying that each word, we assume that even if we don't see in our training set, it appears at least epsilon times in our document for each class. So it's as if we add an additional document where each word appears epsilon times in each class, and we treat it as additional training material. We can show, but we will not, that this is an approximation of a Bayesian model. We have discussed why Bayesian models are able to address the problem of zero counts for the head tossing problem. The idea is the same. We will not discuss the Bayesian problem, but this can be seen as an approximation of a Bayesian model that introduces assumptions that allow us to treat also the cases where the word does not appear in the document, but that doesn't mean that it cannot appear in a test document. Here you have the details if you want. It's called maximum the approximation is a maximum a posteriori estimate of a Bayesian model that uses what is called the Dirichlet prior distribution. But as I said, this we will not see. Now, to improve the model, rather than considering just single words that we said ignores correlations of words, we can extend the model to consider not just single words and the number of appearances of single words, but sequences of words. So, for example, we know that after the word how, typically we have the word are. So rather than having a dictionary where we have just the words of the English, we have a dictionary where we have also the pairs of possible words of the language. So we consider all possible pairs, and we model the probability of the pairs. This takes into account the correlations. Again, through a multinomial model, this is called n-gram model, because if we use the multinomial representation of the problem, rather than working with the sequence of pairs as if they were token, we will do what? We will count the number of times each pair appears in the documents of a class. This will be our new vector of occurrences. This is called n-gram vectors, where n is the length of the sequence that I'm considering, and this allows to take into account partially the correlations, at least for words that are adjacent. Of course, it will not take into account correlations between words that are distant inside the utterance, because it will also only consider sequences, short sequences of words. Okay, this we already said everything, so I think that's all. Questions? Okay, then for today, for this part, it's all.